So today we're going to be talking about molecular molecules and ultimately going from our two-dimensional Lewis dot structure where we have the connectivity to trying to project what that Lewis dot structure looks like in 3 dimensions. And ultimately this is what we call the molecular structure. And molecular structure is important for us because it'll tell us essentially what type of molecules it interact with. It provides information about the physical properties of the molecules that we're ultimately interested in. So today, at the end of this video, or end of this short video, hopefully we'll be able to draw Lewis dot structures in 3 dimensions and be able to approximate the bond angles between 3 different atoms. So here is essentially what we would create based on the Lewis dot structure for methane. So again, we would draw all of the carbon-hydrogen bonds looking exactly like each other, and again, typically going out in 4 different directions. So as this is drawn, it's implied that essentially the bond angle that exists between these carbon, this hydrogen, carbon, and hydrogen, it implies that this is 90 degrees. And hopefully we realize that this isn't necessarily the case. In reality, the bond angle that's drawn is actually different. But in order to actually draw things in 3 dimensions, we have to essentially establish a couple of quick conventions. So the 3D representation looks like this on paper. I have my model of methane right here. So this is what it looks like. It's a little hard to see the depth perception a little bit here. So get my stylus out of the way. So this is essentially what it looks like in 3 dimensions, right? So, oops. So ultimately, we have something that's coming out towards you and something that's going away. So you'll notice that we've basically taken straight lines and then converted them into a dash and a wedge. So this dash and wedge essentially indicate things that are going out towards us and the things that are going away. So the wedge is the thing that's coming towards us. So if we're looking at the model, this is the thing that's coming towards us. And the dash is the thing that's going away. An easy way for me to remember this is basically if you were to think about you in standing up with your arms going out, think about the plane of the board or the plane of the molecule going basically right down the middle of your body. So the wedge is the thing that's coming out towards you. So again, if I were to angle in this direction, this is the thing that's coming towards you. This is the wedge, and my arm that's going back into the plane of the board, that's what we call our dash. Again, this indicates that we don't have everything in the same plane of the board. But everything that's drawn with essentially just a single dashed or wedged line, that's all in the same plane. So again, this is what we call molecular geometry, and how we actually physically generated this molecule here was through what we call valence shell electron pair repulsion theory, or sometimes referred to as VSEPR. So let's talk about actually how we got there and what is the underlying principles of VSEPR. So the underlying principle is actually in the name. So the idea that valence shell electron pair repulsion theory tells me that electrons don't necessarily want to be next to each other. So what they're going to do is try to occupy a space that's as far away as possible. So again, if we go back to our methane molecule, notice that my 2-dimensional structure looks like this. I have what are essentially called 4 electron domains. And so that's basically wherever I have an area of electrons. So I'll just number them here to identify the different domains. So essentially I have 4 bonds. So those are my 4 different electron domains. So if I have a situation where I have 4 electron domains, my angles between the hydrogen, carbon, and hydrogen are going to be 109.5. So again, this angle here is going to be 109.5 in the 2-dimensional. So what it really looks like in 3 dimensions is this angle here. That's the angle, again, between any of the 3 atoms in methane. And the name that we give to this structure, or this 3-dimensional shape, is called tetrahedral. If I have 3 electron domains, so say I have this formaldehyde. So here's what my formaldehyde structure looks like on my model. So this is, again, the 3 electron domain areas are around the central carbon. So we count the double bond between carbon and oxygen essentially as 1 domain. Sorry about that. So this here is essentially 1 domain. And then the remaining 2 carbon-hydrogen bonds are my remaining domains. So I have 3 domains around that central carbon. The bond angle between them is going to be 120, and we call this trigonal planar. The reason why we call it trigonal planar is we can see essentially a triangle that exists between my oxygen, hydrogen, and carbon. So right in my very poor drawing here, I've drawn a triangle. So ultimately the reason why it's called trigonal planar is that if I orient the molecule here, we'll notice that essentially all of my atoms exist in the same plane. So all of my atoms exist in the same plane. If I were to orient them in this direction, I create essentially a triangle. That's why it's called trigonal planar. My last area here is essentially if I have 2 electron domains around a central atom. So this is acetylene. So this is a carbon-carbon triple bond. Again, I can identify the different electron domains that exist here. So if I look at this carbon here, I have 1 electron domain, which is my entire triple bond here. And I have the second electron domain, which is the carbon-hydrogen bond. So again, that's 2 electron domains. The angle between the carbon, hydrogen, and carbon is 180 degrees. And the name we give to that is linear. So again, basically the way to remember that is it's just a straight line between carbon, hydrogen, and carbon. So again, if we're looking at essentially this angle here, so this angle between carbon, hydrogen, and carbon, that's the thing that's 180 degrees. So now what we need to do is essentially take into account the lone pair of electrons. So on the previous slide, the carbon or the electron domains that we were looking at did not have a lone pair of electrons around them. The reason why we want to account for these lone pairs of electrons is they have slightly different orientation associated with them. So if I were to count the electron domains existing in these molecules, the central atom will all have 4 electron domains. But notice that my bond angles have changed. So on the previous slide, we said that the bond angle for this molecule is 109.5. We call that shaped tetrahedral. However, if I have a single lone pair of electrons, that changes the bond angle around my central atom. So we have essentially slightly different names associated with these different angles. Again, all of them have 4 electron domains, but the bond angles are slightly different. So the way that we can memorize this, or the way that we can apply this, is if we have 4 electron domains and no lone pairs of electrons, like we have with methane here, that is going to be tetrahedral and will have this shape that we saw previously. If we have 4 electron domains with a single lone pair of electrons on that central atom, we call that trigonal pyramidal. So this is different than trigonal planar because essentially, if I were to look at the 3-dimensional shape of this NH3, we would actually create a pyramid. So again, if I were to draw essentially the shape here around this, I'm not going to try because my 3-dimensional orientation here for a pyramid would not be very good. But ultimately, this creates a pyramid at this position. So again, this is different than trigonal planar. The reason why this is different, this is 4 electron domains, whereas the trigonal planar is only going to have 3. And then if I have 2 lone pairs around the central atom, for example, water, this is what we call a bent geometry, and it'll have a bond angle of roughly 104.5. So again, we have to identify the number of lone pairs and the number of bonds around that central atom to identify both the angle and the name associated with it. So to kind of quickly summarize, ultimately, valence shell electron pair repulsion theory, or VSEPR theory, is defined by the number of regions of electron density around our central atom. Those numbers, which we sometimes refer to as the steric number, provide both the geometry and angles that we see with our molecule. And remember that the lone pair of electrons is going to modify that angle, and ultimately that lone pair of electrons occupies slightly more area than the bonding electrons. And that's why we see a slight difference in the angles of those corresponding geometries. So to quickly review, if we have a steric number of 4 with 4 bonding regions, we would call this tetrahedral. So an example of that was methane and CHCl4. If we have a steric number of 4 with 3 bonding regions and 1 lone pair, we call that trigonal pyramidal, and the bond angle is roughly 107. Again, a steric number of 4 with 2 bonding regions and 2 lone pairs, we call that bent, and the bond angles around that central atom will be 104.5. Water is an example of that. If we have 3 bonding regions, or essentially a steric number of 3, we would call that trigonal planar. The bond angle around that would be 120. And then lastly, if we have a steric number of 2, or 2 electron domains, we would call that shape linear. So what I suggest you do is to take these examples on the right-hand side here and practice drawing the 3-dimensional structures for each of these.